Hello and welcome to my channel, Hardware.ai. A while ago I made a video on semantic segmentation with new Raspberry Pi HD camera module. I used MobileNet V1 backend SegNet Basic for segmentation task, and I was running rather slow on Raspberry Pi 4, which was noticed by people in the comments. I had to admit that Raspberry Pi 4 is not the best SBC for machine learning tasks, since it doesn't have a hardware accelerator that can be used to speed up the inference, and has to rely on CPU. Since then, I have been working on applications for Raspberry Pi 4 compute module inside reTerminal, some of which included machine learning demos, such as age, gender recognition, object detection, face anti-spoofing, and so on. Here is a list of 4 techniques that can be helpful when aiming for running real-time model inference on Raspberry Pi 4. Ready? Let's go! So, number 1 is designing smaller networks. If your goal is simple enough, for example, image classification less than 100 classes or object detection less than 10 classes of objects, a smaller network can achieve acceptable accuracy and run very fast. For example, MobileNet V1 Alpha 0.25 YOLO V2 network trained to detect only one class of objects, faces, achieves 62.5 FPS without any further optimization. So here are results for two models that I used for as baselines here. You can see them on the screen. This is without any optimization on regular Raspberry Pi 4. The second method is quantization. Quantization is a process of reducing precision for neural network weights, usually from floating point 32 to integer 8. It reduces the size by factor of 4 and latency for 60 or 80% using regular TensorFlow Lite kernels. There are 2 kinds of quantization process in TensorFlow: post-training quantization and quantization-aware training, or QAT. Post-training quantization usually brings a small accuracy loss, which can be minimized if you use QAT, a quantization-aware training. In the process of fine-tuning network with QAT, there are fake quantization nodes inserted to the network, and that allows fine-tune the network and prevent a significant accuracy loss during quantization. For further reading, have a look at TensorFlow Lite documentation and the convert.py script of Accelerate, my personal project that simplifies training of common computer vision networks for inference on embedded devices. So here are benchmark results for 2 baseline models with TensorFlow Lite integer 8 inference. As you can see, we have we have noticeable sped up, especially for larger models. Number 3 is using optimized kernels. Inference speed can be further improved by utilizing frameworks that have operation or op kernels optimized for specific CPU instructions. For example, Neon SIMD, single instruction multiple data, instructions for ARM processors. Examples of such frameworks include ARMNN and XNNPACK. ARMNN SDK is a set of open-source software and tools that enables machine learning workloads on power-efficient devices. The description and provided benchmarks look promising, but the installation procedure on the latest Raspberry Pi OS is painful at the moment. The only proper way you can install the latest version of ARMNN currently is cross-compiling from the source on your computer and then deploying to Raspberry Pi. There are binaries available for Debian Bullseye, but Raspberry Pi OS is still on Debian Booster. The inference test results with my benchmark scripts were mixed. For single modal, it showed worse performance than vanilla TensorFlow Lite, but it turned out to be faster in multimodal inference, possibly due to more efficient multiprocessing utilization. So here are results for ARMNN floating point 32 inference. And in a few moments, I'm going to explain why I only have the results for floating point 32 and not integer 8. So let's talk for now about another optimization framework called XNNPACK. It's a library for accelerating neural network inference for ARM, x86, WebAssembly architectures on Android, iOS, Windows, Linux, and macOS environments. So it's officially supported by Google, and it's integrated in TensorFlow Lite as a delegate, which is enabled by default for Android builds, but for other environments, it needs to be enabled manually. So if you'd like to use XNNPACK on Raspberry Pi 4, you'll either need to build TensorFlow Lite pip package, the interpreter, by yourself, or download one of the third-party binaries. I will leave build instruction and pre-built binary for you in the article, which you can find, the link to which you can find in the video description. So here are XNNPACK results, XNNPACK delegate, TensorFlow Lite, floating point 32 inference results on my two baseline models. The main problem with these optimization frameworks and optimized kernels is the uneven support of different architectures and neural network operators, and also the precision types in different networks. For example, integer 8 optimized kernels are work in progress both in ARMNN and XNNPACK. The support for integer 8 optimized kernels in XNNPACK for ARM was added recently and seems to bring modest performance improvements of about 30% depending on operators used in your model. And you can check the list of operators available if you go to README of XNNPACK or ARMNN, and then you'll be able to roughly see before testing how much improvement can using this particular framework bring for your specific model by comparing the operators supported and operators in your model. So while researching the accelerated model inference on Raspberry Pi and ARM processors, I stumbled upon another promising lead in TensorFlow Lite GitHub PR, pull request, adding optimized kernels for dynamically quantized models. So I left the link in the video description, have a look. So it was really promising. The author said that he was able to achieve 3 to 4 times latency improvement. There is another PR that allows more convenient usage of these optimized kernels. It's in development currently. And the fourth way is pruning of networks and sparse inference. Pruning is the process of fine-tuning trained neural network to find the weights that do not contribute to correct predictions and removing them. Pruning is very helpful for reducing the size of the model for compression by simply setting the dead weights to zeros, but using it for reducing latency is trickier since it requires removing the connections themselves, which can lead to significant accuracy loss. Using TensorFlow Model Optimization Toolkit, experimentally, it was possible to achieve up to 80% sparsity with negligible impact on accuracy. This is according to Google AI blog article, that's a link to which I will leave in the video description, and my own blog article. You can have a look at the results, but of course it will also depend again on the model architecture. And also have a look at the guide to pruning and sparse inference with TensorFlow Lite Model Optimization Toolkit. It is work in progress, like many other techniques that I mentioned today, so not all the model architectures are supported yet. So to summarize all of that, the fact that the board does not have a dedicated hardware to accelerate neural network inference does not mean it's useless for machine learning. There are some optimization options that allow achieving acceptable inference speeds. Applying some of these techniques, such as optimized kernels, can be a bit tricky though, and requires some tweaks to the model architecture and possibly combining the inference optimization packages from source. And since a lot of optimizations are currently on the bleeding edge of development. Oh, and while you're at it, make sure you avoid thermal throttling when running optimized inference, especially multi-threaded on Raspberry Pi 4. Get yourself one of these nice cooling towers and don't set your Pi on fire. Until the next time,